Okay, today we're going to be discussing how we can tell if two things are conjugate pairs. So you can have a conjugate acid base pair or a conjugate base acid pair. And really, the word conjugate doesn't matter. The question is, do you have pairs? So every acid has a conjugate base, or you could say every base has a conjugate acid. So we want to know, if I give you an acid, what is its conjugate pair as a base? Or if I give you a base, what is its conjugate pair as an acid? And we want to recognize when we have conjugate pairs, okay? And we want to understand what that information can give us, okay? So if we're given an acid, we want to know what its conjugate base would be, and then we can know more information. Okay, so there's going to be a couple of situations where it's really important to know that you have conjugate pairs, or recognize two different things as conjugate acid base pairs, so you can figure out more about the solution. All right, so let's just review our rule for conjugates. All right, so remember, I wrote this on the board the other day. I said a conjugate blank of a weak blank is a weak blank. Okay, so number one, if we follow this rule, we can use the word acid or base and fill it in the blank, but we have to alternate. So if I put acid here, I put base here, and then I put acid here. Okay, or if I put base here, then I put acid here, then I put base here. And that's a rule to follow. So the deal is, if you have a weak acid, whatever its conjugate pair is going to be a weak base in solution. Okay? Or if you have a weak base, whatever its conjugate pair is, it will be an acid in solution. A weak acid, but it'll still be acidic. All right? So let's put this rule to the test here. It says, so if we follow the rule, the conjugate acid of a weak base is a weak acid. All right. So if we know that NH3 is a weak base, which it is, right? Ammonia is a weak base. Then if we can figure out what its conjugate acid is, which is NH4 plus, or its conjugate pair, NH4 plus, we know that NH4 plus is a weak acid. So if I throw ammonium into solution, my solution is going to be acidic, because I know it's a weak acid. And the reason I know it's a weak acid is because I know it's the conjugate of ammonia, and I know ammonia is a weak base. Now, ammonia is a common one that you'll memorize as a weak base. But if you are told X is a weak base, then its conjugate pair, whatever its conjugate pair is, would be an acid in solution. A weak acid, but still an acid. Okay? And it's flipped. So the conjugate base of a weak acid is a weak base. And so if we did it the other way around, if I told you that ammonium was a weak acid, then you would know its conjugate base, which is ammonia, would have to be a weak base. All right? So, and again, it really doesn't matter of the two things, of the pairs that you're comparing. It doesn't matter which one you call the conjugate and which one you call this the regular thing. We could say ammonium is an acid, and ammonium's an acid, and ammonia is its conjugate base. Or we could say ammonia is a base and ammonium is its conjugate acid. It really doesn't matter. That word conjugate doesn't matter. It's just, do you have acid-base pairs? And we need to know if they're weak. If they're weak, they're both weak. All right? So the other rule to kind of memorize here is the conjugate pair. And notice I'm using the word pair here instead of acid or base, because the conjugate pair of a strong acid is not acidic or basic in solution. It's neutral in solution. So chloride is going to be neutral in solution, and the reason why chloride is going to be neutral in solution is because its conjugate pair is a strong acid, HCl. Okay, its conjugate pair is HCl. Okay, so you could call chloride the conjugate base of HCl, and that's true. Like, chloride is the conjugate base of hydrochloric acid, but I don't like to use the term conjugate base in this case because chloride is not a base. Chloride is neutral. Adding just chloride to your solution is not going to make your solution basic, okay? And so that's why I'm saying the conjugate pair. But the conjugate pair of a strong acid, so if we list our strong acids, right? HNO3, HCl, HBr, HI, H2SO4, HClO4, HClO3. Really what we're saying is these anions, nitrate, chloride, bromide, iodide, sulfate, perchlorate, chlorate, those ions are neutral in solution. They're neutral in solution because they would be the conjugate, technically they're the conjugate bases, but I would just call them the conjugate pairs of strong acids, okay? And now we can kind of follow the rule. I know that fluoride would be a base, a weak base, because you know HF, its conjugate acid, is a weak acid, all right? So if I put chloride in solution, if I put sodium chloride in solution, the solution is going to end up being neutral. But if I put sodium fluoride into solution, the solution is going to be basic because I need to recognize that fluoride's a base, right? Okay. So let's understand why we need to be able to identify conjugate pairs and the information we can get when we know we have conjugate acid-base pairs, all right? All right. So why do we need to know the pairs? This is number one, okay? You're given more information when you know you have conjugate pairs because this is an equation that we got to follow, okay? This equation's on your formula sheet. It says Ka times Kb equals Kw. Now, let's understand, it's not any Ka of any weak acid times any Kb of any weak base equals Kw. The acid and the base in this scenario has to be conjugate pairs. So we could say, if I know the Ka of acetic acid and I know the Kb of acetate, which is its conjugate base, those should multiply and equal Kw. And we know what Kw is. It's 1 times 10 to the negative 14, all right? So this equation is true when the base is a conjugate pair of the acid, okay? So the Ka of so let's understand what this means. It means, let's say I'm given the Ka of HF, which you should know is a weak acid, right? Okay. That means if I was given the Ka of HF, I can find the Kb of fluoride, its conjugate base. But the Ka of HF times the Kb of F minus will always equal 1 times 10 to the negative 14. It will always equal Kw, all right? So we know if you're given a Ka of a weak acid, and again, you would only be given a Ka for a weak acid because strong acids don't get a Ka value, right? If you're given a Ka of a weak acid, you're also given the Kb of its conjugate base. Just indirectly. You got to recognize that, all right? So let's say we're told that the Ka of acetic acid is 1.8 times 10 to the negative 5, all right? We have to know that indirectly, the question's giving us the Kb of acetate, okay? So all I was given was this. We need to look at acetic acid and know what its conjugate base is, which is just acetate, C2H3O2 with a 1 minus charge. And I know that because this is a weak acid, that its conjugate pair, acetate, is a weak base, right? The conjugate of a weak is weak, okay? But I can use this equation to solve for the Kb and just see how weak of a base it is. All right, remember, the higher the Ka, the stronger the acid, the lower the Ka, the weaker the acid. The same thing's true about Kb. The higher the Kb, the stronger the base, the lower the Kb, the weaker the base. So, you know, acetate's a base. It's not a very strong base. It's a weak base. It's a very weak base. But I know it's Kb now because I was given the Ka of its conjugate pair. All right. So again, let's understand. I was given the Ka for acetic acid, but now I know this too. Maybe I need that in a question. Maybe in part A of a question, I need to know the Ka of acetic acid. But then in part D, I need to know the Kb of acetate. Well, hey, they gave it to you. You just got to know how to spot it. Okay? All right? And it works the other way, right? Like, let's say you're given the Kb of a weak base. So you're told that the Kb of NO2 minus is 2.5 times 10 to the negative 11. Now let's understand something. Maybe you don't know NO2 minus is a weak base. But if you're given a Kb value for something, that's means you're being told that it's a weak base. If something has a Kb value, it's a weak base. If something has a Ka value, it's a weak acid. So just me telling you that the nitrite ion, not nitrate, nitrite, the nitrite ion has a Kb, you know it's a weak base. Okay, great. But that means we can also use the Ka times Kb equals Kw equation to figure out the Ka for nitrite's conjugate acid, which is HNO2. Okay? So we plug it into that equation, right? We plug in the Kb given to us. Kw divided by Kb will give me Ka. And so I get the Ka for the nitrous acid, okay, HNO2. All right. All right. So let's look. Right here are two conjugate. Here are conjugate pairs: acetic acid and acetate. Here's the Ka for acetic acid. Here's the Kb for acetate. Okay. And then let's look at these two. These are conjugate pairs. All right. So here is the Ka for nitrous acid, and here's the Kb for nitrite. It's conjugate base. And what I want you to notice is, look how, of these two acids, the nitrous acid is going to be a little bit stronger because it has a higher Ka, 10 to the negative 4 versus 10 to the negative 5. But notice, the stronger the acid, the weaker its conjugate base is as a base. Okay, because compare. So of these pairs, this pair has the stronger acid than that, but this pair, this pair has the stronger acid. Sorry, the nitrous acid is stronger. Okay, so this has the stronger acid. Okay, but this has the stronger base. Notice 10 to the negative 10 versus 10 to the negative 11. Okay, so notice the stronger the acid, the weaker the conjugate is of the base, and it would be flipped too. The stronger the base, the weaker the conjugate acid is as an acid. Okay. All right, so it's important to understand that. So given an acid's Ka, you know you can also calculate quickly the Kb of its conjugate base, or given a base, in the Kb, you could use a simple equation to find the Ka of its conjugate acid, right? But we really need to know how to spot conjugate pairs, right? And so let's say you're trying to find the conjugate base of an acid. Well, remember, an acid means, if something's an acid, that means it's a proton donor, right? It's losing a proton, right? And if it's an Arrhenius acid, that means it's losing a proton to water, okay? That doesn't really mean anything right now, all right? If I want to know an acid's conjugate base, all I have to do is remove an H plus from it. You take an H plus away from it, whatever it turns into, that's its conjugate base. So if you're looking for a conjugate base, remove an H plus, right? So if I'm telling you this is an acid and I want its conjugate base, take an H plus away, what do you got? SO4 2 minus. That's its conjugate base. So these two are conjugate acid-base pairs. So the Ka of this times the Kb of this would equal Kw, right? All right. What if this is my acid, HCN? Take an H plus off, what do you have? Cyanide, Cn minus, right? These are conjugate acid-base pairs. So the Kb of cyanide times the Ka of hydrocyanic acid is going to equal Kw, right? Carbonic acid, a weak acid. Take one H plus away, and what do you get? You get HCO3 minus. So this acid is conjugate base pairs with this base. But notice this can also be an acid. So this has a conjugate base pair as well, okay? When this is a base, this is its conjugate pair. But when this is an acid, this is its conjugate pair, okay? So the Kb of carbonate times the Ka of HCO3 minus, hydrogen carbonate, would equal Kw, but then the Kb of hydrogen carbonate, so this acting like a base, times the Ka of carbonic acid would equal Kw. All right. So these two are pairs and these two are pairs, but in this pair, this is the base and that's the acid. In this pair, this is the acid and that's the base. Okay. So if you want to know a conjugate base, you take an H plus away. All right. Well, how do you figure out a conjugate acid? You add an H plus. Okay. So you add an H plus to it, and whatever it turns into, that's its conjugate acid. It's pretty easy, right? So F minus is a base, HF is its conjugate acid pair. I added an H plus. And notice the charge, guys, that means something, right? This is F minus and I add an H plus, so now it's neutral, right? If we go back up here, I took away an H plus, so now I go from 1 minus to 2 minus. I'm neutral here, I took away an H plus, and now I'm 1 minus, right? I'm neutral here, I took away an H plus, and now I'm 1 minus. So understand how that works, all right? So if this is a base, add an H plus to it. There's its conjugate acid, okay? Water can act like an acid or a base. Same with this, right? We could take an H plus away and you get sulfate, and that's its conjugate base pair, but as a base, this is its conjugate acid pair. So water as a base, add an H plus to it. Hydronium is conjugate acid to water's base, right? All right, I wish I drew it, but I didn't. But water also has a conjugate base, right? If water acts like an acid, you take an H plus away, and hydroxide, OH minus, is water's conjugate base, and water's conjugate acid is hydronium. Okay. So let's kind of put this in some application here, all right? Now again, understand you're gonna have to recognize this. It's not gonna be straight right in front of you, this is what you're given, right? All right. So let's say in part A of the question, you were given the Ka of acetic acid. So you say, hey, the Ka of acetic acid is, which is this acid, is 1.8 times 10 to the negative 5. All right. In the back of your mind, you should understand, okay, well, they gave me the Ka of acetic acid, and maybe I'm going to use that for the first, couple questions in this problem. But also, whenever I'm given a Ka, I'm also given a Kb. I just have to calculate it. So understand you have the Kb for acetate. So the question now, when you get to like the third question of the problem, it's like, what is the pH of a 0.1 molar solution of potassium acetate? And you look at that and you're like, potassium acetate? I want to know the pH, and they gave me the Ka of acetic acid, and I'm talking about a salt dissolving in water, potassium acetate, right? So what you have to recognize is that potassium acetate in solution is really K plus and acetate ions. And we have to recognize that, wait a minute, we don't care about metallic ions or neutral. So potassium ions, sodium ions, lithium ions, aluminum ions, calcium ions. If it's a metallic ion, that means nothing to me. And really what we're looking at is the anion here. And that is the conjugate, that's the anion of a weak acid. It's the conjugate base of a weak acid. So it's a weak base. So in a solution of potassium acetate, it's going to be basic because acetate's a base. So to answer this question here, what's the pH of this solution? We don't need the Ka of acetic acid, we need the Kb of acetate. But we have to recognize that acetic acid and acetate are conjugate pairs, so we have the Kb of acetate, okay? So we plug it into our equation, we get the Kb. So really the question is, hey, what's the pH of an acetate solution that has this concentration, and the Kb of acetate is 5.6 times 10 to the negative 10, all right? So that's the question spelled out for you. That's what you need to figure out, right? But it was kind of disguised. They gave me a Ka, they gave me a salt that really has nothing to do with that Ka, or wait, does it? And yes, it does, right? It's the weak of a weak, the conjugate pair of a weak acid is a weak base. And in this case, we have to recognize that acetate would be a weak base because it's the conjugate base of acetic acid, which is a weak acid. And we have to understand that if I'm given a Ka of an acid, then I can calculate the Kb of its conjugate base, blah, blah, blah. All right, everything we just said, all right? So now we can just, this question is just a weak acid, or sorry, a weak base, a Kb shortcut. right? So we use our KB shortcut. We say KB equals X squared over the initial concentration of the base, and the base in this case is acetate. All right, we figured out the KB, we were given the initial concentration, right? If we wanted to make this better, we could say 0.1 minus X, but we're gonna 5% rule that X, right? And so we solve for X, but whenever we're using our KB shortcut, we gotta recognize that X is the hydroxide concentration. So we solve for X, and if we get the hydroxide concentration, we're just 2 calculations away from the pH, right? We take the negative log of hydroxide to get the pOH, and then 14 minus that would give us the pH, all right? All right, so that's one reason why we need to be able to identify conjugate acid-base pairs, right? That's one reason we need to be able to identify conjugate acid-base pairs, because of questions like that, right? We want to start recognizing things as acidic or basic in solution, or neutral. So I know metal ions are neutral, and I know like chloride's neutral and nitrate's neutral, and iodide is neutral and bromide's neutral, because those are conjugate pairs of strongs, and conjugate pairs of strongs are neutral. But now I know all these other anions are weak bases. I know acetate's a weak base. I know carbonate's a weak base. I know fluoride's a weak base. I know sulfite is a weak base, right? Because those would all be anions or conjugate pairs of weak acids. And the conjugate of a weak is a weak, so the conjugate pair of a weak acid is a weak base. And so now, you know, when I dissolve sodium acetate in solution and I wonder why my solution's basic, you don't have to wonder anymore. Acetate's a base. And I know acetate's a base because its conjugate pair, acetic acid, is a weak. And so that means acetate is a weak, right? Okay. All right, and so the next step up from this in recognizing when we have conjugate acid-base pairs is this is how we make what we call a buffer solution, okay? So what we're gonna learn later on when we get to 5-3, okay, when you have both of these things in solution, when you have both conjugate acid and its base, or conjugate base and its acid in solution at the same time, we make what we call a buffer solution. And we're going to talk about what that means. But all a buffer solution is when you have a weak acid and its conjugate base in solution, or a weak base and its conjugate acid in solution. All right. So if I took a solution of HF, which has HF in solution, right, and I added some sodium fluoride, which really means I add some fluoride to the solution, I would have both HF molecules and fluoride molecules in the solution at the same time. I really should have said fluoride ions. HF molecules and fluoride ions in solution at the same time. If you recognize that those are conjugate acid, weak base, and acid pairs, now you know you have a buffer solution. Okay, and we're gonna talk about what that means, what buffer solutions do, what they're good for, what the benefit of knowing if you have a buffer solution or not is, and how to make one, and we'll make one in lab and all that stuff. But anyway, it's important to really recognize this conjugate acid-base pair stuff, because the sooner you spot that you have conjugate acid-base pairs, the more you know, right? So like, I'm given a KB, so now I have a Ka. I'm given a Kb of a base, but I'm also given a Ka of an acid. It's just got to be its conjugate pair, right? I'm given the Ka of an acid. I know I'm also given the Kb of its conjugate base. I got to know what its conjugate base is. So if I'm given an acid, take an H plus away, that is the identity of its conjugate base. If given a base, add an H plus to it, that's the identity of its conjugate acid, right? And then moving forward, we're going to be talking about those buffer systems. So knowing conjugates and knowing that rule is, you know, the conjugate of a weak is weak. Now we start understanding why this ion is neutral in solution, but this ion is basic, or this ion is acidic, okay? Because we understand that rule. The conjugate of a weak is weak, and the conjugate pair of a strong is neutral, okay? So we'll spend more time on it, but that's, you know, the lesson I wanted us to focus on today, all right?